Hello everyone, I'm Kyriakos Koutikos, and today I'm going to present to you a presentation about smart service discovery and selection framework for BPaaS allocation. This is how I look like. I'm a researcher at ICS 4th, and some details about today's webinar is that the introduction is that I speak and you cannot speak, you cannot say anything, so all microphones are muted. But in the end, there will be a small session for 5 or 10 minutes where you can place your questions in the chat window on the bottom of your screen. So I start immediately with the agenda of the webinar. First, I will identify what is the main problem. I'll provide an overview of the solution, and then I will analyze the two parts of the solution. I will then move on to a demo. I will finally summarize the presentation, and then I will wait for your questions. So let's start with the problem. As you have seen in the previous webinar, which concerned the BPaaS allocation environment, the broker has to manually select cloud services at different levels. So he has to select SaaS services in order to realize the functionality of service task in the BPaaS workflow, and he has to also discover AI services in order to support the deployment of respective internal service components of the BPaaS workflow. So while let's say it can be easy to manipulate a very small set of service tasks and respective mappings, things can be more difficult when a large solution space has to be explored. And usually, as a particular optimization problem has to be solved in order to correctly and optimally select a set of cloud services that can realize the BPaaS workflow, then it's impossible for a human to do this exploration, and he has to have appropriate tool support. Apart from this issue, actually the dependencies between the different levels have to be taken into consideration for the following reason. So if you select, let's say, an IaaS, in order to just service, in order to realize in order to deploy a particular internal service component, then this selection at the IaaS level can influence the selection at the SaaS level, because this selection will map to particular performance level that will be delivered by the internal service component, which will influence then the selection of the rest of the SaaS services at the SaaS level. Apart from this, you can have, let's say, some particular design choices which can be involved. For example, for a particular service task, there can be two options. You can either use an external SaaS in order to realize its functionality, or you can deploy a software component as an internal SaaS in order to realize this component, this task functionality, and that component will need to be deployed in a particular IaaS service. Apart, let's say, from these three main issues which map to the manual selection of the cloud services, if we check the state of the art and the respective tools in the market, then you can see that most of the cloud service allocation frameworks deal only with one level. So they don't take into consideration the dependencies between the different levels. And in addition, they exhibit low accuracy because they don't consider semantics or more formal approaches for service discovery and selection. So what is our solution is that we propose a smart service discovery and selection framework. And this framework, as you can understand, covers two different functionalities. The first one is that it delivers semantic service discovery in order to cover both functional and non-functional aspects and increase the accuracy. And this actually leads to having the ability to discover services at different levels of abstraction. And the second functionality is the cross-level service selection, which can be used in order to identify the best possible or optimal solutions by considering not only the dependencies between the levels, but also different kinds of user requirements. So deployment requirements, location requirements, non-functional requirements, including response time, availability, and so on, and cost requirements. What is the benefit of this solution is that it automates the service selection process, and this leads in the end in the acceleration of the bundle development time, and gives the opportunity to the broker to bring in more rapidly BPaaS bundles in the market. Here is an overall architecture of the framework. So you can see that there is SDS service, as we call it, some smart service discovery and selection service, which wraps the functionality of the two main modules of the service discovery and the service selection module. In principle, the front-end user interface, which is another component, could be the user interface from the evaluation environment, and we are currently investigating how this integration can be performed. But in the demo that I will show to you later on, a very simple interface has been developed just for demonstration purposes. And of course, somebody can build more sophisticated interfaces on top of this SDS service. Now let's move on analyzing each part of the main solution, so the service discovery and service selection. So the service discovery module, it's quite configurable because it's able to exploit different aspect-specific matchmakers, where aspect-specific means functional or non-functional. So if we consider the functional aspect, then we rely on a state-of-the-art functional matchmaker, which is called Alive, and we also exploit our work concerning the non-functional aspect, and this maps to two different kinds of approaches. In the first approach, we are using ontologies and especially particular techniques from semantic web called ontology subsumption in order to perform the matchmaking, while in the second kind of approach, which is called mixed, we rely on ontological specifications of non-functional specifications of services, and first we perform alignment of these specifications based on their quality terms. Then we transform these specifications into constraint problem models, and then we solve these models in order to infer the matchmaking. In this presentation, I will focus more on the functional matchmaker and on the ontology-based non-functional matchmaking approach. In addition, we are now investigating how aspect-specific matchmakers can be combined in innovative ways. And one conclusion that can be also inspected in reference 4 is that the best possible combination for now is the parallel combination. So we have first to execute in parallel both the functional and non-functional matchmakers. Actually, in our implementation, we allow the user in a configurable way to specify which composition is desired by him. So we can have sequential compositions, parallel compositions, and some more advanced kinds of compositions for the aspect-specific matchmaking. Here's architecture of the service discovery module. So as you can see in the figure, we start with the specification processor, which takes as input the user requests in the form of a particular specification, and this processor initially attempts to align the specification based on a particular term ontology store. Once this alignment takes place, then the compositor takes responsibility of realizing, let's say, the user request by composing the different aspect-specific matchmaking systems. But this is done in a quite transactional manner. So this means that if we want to, let's say, to register a particular service advertisement, and the functional part has been successfully registered, but the non-functional one has not, then we can revert back to the previous system situation by unregistering the functional part of the advertisement. And of course, this compositor also is able to be configured in order to apply particular composition logic based on the different kinds that was mentioned in the previous slide. So it can enable the sequential, parallel, or more advanced composition of the matchmaking, of the aspect-specific matchmaking systems. And I would also like to say that here that these subsystems are extensible in the sense that you can use different matchmakers in order to realize the respective functionality. And the only assumption that we impose is that these systems should be able to support the main languages that are used in the system, which is OLS for the functional specification of services and OLQ for the non-functional specification. Now let's move to the functional matchmaking. This type of matchmaking relies currently on the semantic input-output matching and on the textual similarity of the service specifications. And it employs smart indexing mechanisms in order to speed up the matchmaking process, and which also are quite robust to change. Actually, there are 5 main categories of results that can be produced via this functional matchmaking, which has been also proven in the past that it leads to increased accuracy in the service matchmaking process. So we have the perfect match, in which the service request perfectly matches the service advertisement, and this means that both the request and the advertisement have the same input-output parameters. And then you have the plugin match, which means that the service input, every service input subsumes a particular request input, and its request output either is the same or is an immediate super concept of the service output. We have subsumes matches where the service, each service input subsumes a particular request input, and its request output subsumes a particular service output. And then you have the nearest failure match, which is a kind of a lower level from the subsumes match, where also we take into consideration the textual similarity and a threshold imposed on this similarity in order to infer the matching. And then the final level, which is the failure one, indicates that there is no match between the service and the user request, so the service is put on this failing category. Concerning the non-functional ontology-based matchmaking, we actually focus on different reorganization structures in order to speed up the matchmaking and registration process. And in this respect, we have developed different variants that rely on its different structure that has been devised. But the core matchmaking in its variant is the same. So we use ontology using subsumption techniques in order to infer whether the non-functional request subsumes the non-functional offer. Where subsumes means that the solution space of the request includes the solution space of the service offer. In the focus of analysis here, we consider now the variant of a subsumes-based matchmaking approach, where the advertisements are organized in subsumption trees, where the root of such a tree subsumes all its descendants. In this kind of organization, the matchmaking is performed as follows. We try to compare the request with its tree root, and if there is a match with a particular tree root, then all 3 nodes are also matched with this request. We have to inspect them and match them with that request. In this way, we reduce the number of comparisons we have to perform. Otherwise, if we don't find a match, then we have to go deeper into the tree recursively in order to find out those nodes that are matched by the request. Here you can see a particular example of how this matchmaking can be performed. So as you can see, you have the request colored in blue, and then you have 3 trees, where the 2 trees, let's say, have also additional descendants, while the last one has only 1 member. So as you can see, we will compare first the request with offer 1. It will be subsumed, this will be subsumed by the request, and then it will not need to go down to in this tree to compare the request with offers 11 and 12. Then if you go to the second tree, we will match the request with the offer 2, and we'll see that there will be no match, so we'll have to go deeper into the tree, and then we'll compare the request with offers 21 and 22, and we'll see that the offer 22 matches the request, and then we don't have to go down to the descendants of this offer in order to find the matches of this request. So in overall, if you can see, we have, let's say, 1, 2, 3, 4, and 5 comparisons instead of 9, and this actually speeds up the matchmaking time. Concerning the service selection, so we'll go to the second part of the solution. What we try to do is we try to transform the input that is given to the module, which takes the form of user requirements. We wait on these requirements and the abstract service workflow, and in addition the solution space, so all the say advertisements that must make the task of the abstract service workflow. So this input is transformed into a constraint program optimization model, and we use a constraint programming solver to solve it. The interesting features of this module, selection module, is that first it employs smart utility functions for each non-functional metric in order to guarantee feasibility even for over-constrained requirements. So this kind of functions allow a slight, let's say, violation of its user requirement imposed on the respective metric, and in this way we can also be able to provide solutions that other frameworks are not able to provide in this case of over-constrained user requirements. As already indicated, there are some design choices have to be made in the service selection, and we do take them into account by a careful formulation of the constraint optimization model, and you can find more details about this in reference 5. In addition, we are able to concurrently handle the IaaS and SaaS service selection, so cater also for the dependency between these two levels, and this catering involves, let's say, the use of different of functions which try to connect the different levels together. So in this sense, if we deploy a particular component on a certain AI service, then it will be able to infer what is the quality of service of that component, and then it will be able to influence also the SaaS service selection. By using the constraint programming techniques, we are not, let's say, restricted only to the use of linear functions, but also non-linear functions. And these functions can be used not only to connect the different levels together, but also to support the composition patterns that are required in, let's say, in this kind of selection approach. So let's say these composition patterns are required in order to map the individual QS of particular service selected on the SaaS level to the respective QS of the overall service composition. Another feature is that we are able to cover location requirements, and this can take the form of either component collocation on the same virtual machine or in the same cloud, but we are also able to address the opposite requirements, so no collocation of components in the same VM or on the same cloud. We are able to address high-level security requirements, and this maps to an approach where we first, let's say, derive the security controls that can be supported by the cloud providers by a particular questionnaire-based approach, based on the KAIC from a questionnaire from the Cloud Security Alliance, and then by allowing the user to provide a set of security controls that have to be realized by the cloud service providers, then we perform set matching in order to see whether the security controls requested are included in the security controls that are offered by particular cloud. Finally, another feature of the approach is that we are able to save the solution time, and this can be done by fixing models of the model parts of the CP model by exploiting the previous execution knowledge of one BPaaS or similar BPaaSs to the current one. So what we actually do is that we actually use a rule-based approach over a knowledge base, which is constructed from the execution knowledge, and especially from deployment facts and monitoring facts, and then we derive the best deployment based on this rule-based approach, either for the whole BPaaS or for particular BPaaS components. And in this way, we actually map allocation decisions and fix them, and thus, in this way, the complexity of the CP model is reduced, and of course, the solution time is accelerated. Here's the architecture of the service selection module. So we have the service selection controller, which takes care of orchestrating the respective selection logic. And this component actually calls 3 subcomponents, which map to the 3 main tasks that are being involved in the service selection. So the collection of the input, the transformation of this input to an optimization problem, and then the solving this problem by the constraint solver. Now, after presenting, let's say, the framework and its main functionalities, I'm going to showcase to you a particular use case regards the send invoice and BPaaS, which is BPaaS can provide support to SMEs and startups in order to construct and send invoices via email. So this BPaaS contains various, let's say, tasks, but those tasks are mapped to automated functionality, involve 2 main, let's say, systems or services. The first one is the invoice ninja one, which can be used in order to construct an invoice and send it via email. And the other one is the CRM, system of service, which can be used in order to connect to the user base of a particular organization and get the information of those users who will be involved in the invoice construction. Now we consider the situation where the invoice ninja has been put as a software component, and we need to deploy it to a respective ES service. While for the CRM system, we would like to use an external SaaS service. So by considering this BPaaS, the broker will post some kinds of requirements which can be posed on the global or the local level. So at the global level, we have a global availability constraint that availability should be greater than 98%, and that the total price per month for the whole BPaaS should be less than $135. Then we have local-based requirements for the CRM SaaS service, that its reliability should be greater than 0.8, and that its response time should be less or equal to 20 seconds. And for the invoice ninja component, software component, we impose the requirement that it has to be deployed on a virtual machine, has 2 cores, 4 GB of main memory, and 20 GB of hard disk. And its operating system is Ubuntu. Now, consider that we have, let's say, some particular offerings at the SaaS and IaaS level that are able to realize and support functionality of the BPaaS, of the send invoice BPaaS. So you can see on the top table that 3 SaaS are able to satisfy, let's say, the functionality of the CRM service, and they are actually ordered according to the service level. So the first service, Suga CRM, has the best possible service level, mapping to the highest possible values for availability, reliability, and response time. But it is the most costly SaaS service. The second one has the medium, let's say, service level, but it has less price. And the Zoho CRM has the lowest possible service level, but is the cheapest service from the 3. And at the bottom table, at the bottom, you can see that there are 4 VM offerings from 2 cloud providers, which match the requirements of the broker concerning the invoice ninja software component. And you can see that each virtual machine of each provider has a mapping to a respective virtual machine of another cloud provider. So tough to medium has a correspondence to A2B2 from Azure, and F2 point large has expected correspondence to F2 in Azure. But there are some trade-offs with respect to the price. So if you consider the medium level, let's say, virtual machines offerings, then you consider that the Azure offering is cheaper. But if you consider the maximum or large virtual machine offerings, then the Amazon virtual machine offering has a better cost. And of course also availability, as you can see in the table. So based on, let's say, on the requirements and the solution space, then the system will automatically perform service discovery and selection and will derive 4 main solutions that map to the combination of different services. So you can see that these 4 solutions in this table and their respective utility in descending order of appearance. So now I will switch on to the expected demo. So this is a small demo application that has been mapped to this sending voice BPaaS concretization. And on the top, let's say, of this let's say, user interface, you can see how the user can play with his requirements. So for the moment, the availability and cost, let's say, are fixed as metrics on which you can post requirements and preferences. But this application can be customized and extended in order to include posting requirements on different metrics. So as you can see, the user can provide, let's say, weight to its metric and in particular respective thresholds, and then he can just press the allocate BPaaS button, and after this is done, and then he will be able to see the results. So the 4 results that were also presented in the previous table. Whereas here you can see what is the CRM service selected, what is the ES service selected, then what are the availability, cost, and overall utility values. But then if you, let's say, play with the thresholds, then you can actually explore better the solution space and come up with different solutions. So if I change the threshold for the cost, then you will see that the solutions are reduced because some solutions don't satisfy this modified requirement. And then of course the user can play with the weights in order to see differentiation also in the ordering of the solutions. So going back now to my presentation, I will provide you a summary of what has been presented. So we have presented an integrated semantic framework for smart service discovery and selection, which has a very high level of accuracy. It does consider dependencies between the adjacent levels and in particular size and YAS levels and workflow, and caters for different kinds of BPaaS requirements. As I said, deployment, location, cost, performance, and so on. In addition, this framework is ideal for BPaaS allocation, for a BPaaS allocation environment in order to automate the manual selection of services task, and in this way it accelerates the bottom development time. This framework is offered as a service, but as also in the architecture, but is also available as an open source component. And you can see here the respective link of this let's say innovation item, as we call it in the CloudSocket project, and where you can find more information about this framework, and also you will be able to download it and play with it. Until now, this let's say this innovation software is not yet ready, but it will become ready quite soon, and then you will be able to visit it and see also the rest of the innovation items in the project. So this ends my presentation. Thank you all for participating, and now I'll be very happy to answer your questions. So please be free to post them in the chat window. So I will wait for a couple of minutes, and if I don't hear from you, then I will close the webinar. Okay. Okay, so I see already one question being posed from Paul. So, yeah, he's right. So, in order to use the framework, there should be a particular registry of services developed, which includes the semantic description of these services, both with respect to the functional and non-functional aspect. So how to create this registry, yeah, is an issue, I would say. But first of all, there exists some, let's say, registries which already contain some semantic web content. So you can try to build on top of them, let's say, a more extended subsystem, registry system. But in addition, there are also many various information sources from the web where we can create crawlers in order to draw the respective content from them and annotate it semantically via the use of domain ontologies. And after we do that, then we'll have, let's say, a more elaborate service registry via which the BPaaS allocation can be performed. I don't see any other question being posed. So I think I will end now the webinar. I would like again to thank you all for attending the webinar. I hope you find this innovation item, this smart service discovery and selection framework, very interesting. And I will be happy to actually answer any of your questions and so on by if you were able to say to visit the Innovation Shop link and be able to contact me in order to answer your questions. But there you will find all the materials that you would like to have in order to inspect this innovation item. And let's say as a last slide, you can see also my the references that have been mentioned in this presentation, where you can find more information about the research approach that has been followed in order to realize this framework. So thank you very much for attending the webinar.